All right, so if we hop back in the Wayback Machine to last Wednesday, you remember we opened up the concept of molecular shape in the beginning of chapter 5. And we introduced some concepts in here, things like steric number, bond angles, molecular shape versus electron geometry, those kinds of things that are going to inform what we're going to talk about largely today. So what we have to think about as far as electron pair geometry is concerned, these 5 shapes inform what we would call our electron domain geometries. And they're all related to steric numbers. So when our steric number is 2, we will find that we have a linear shape. And again, this should make sense to us. If I have 2 objects and I want to put them as far apart as possible, I'm going to put them in a line, 180 degrees apart. If my steric number is 3, again, if I want to put 3 objects as far apart from each other as possible, in your mind, you're probably thinking triangle. And you would be right. The shape here is triangular. But we have to be a little bit more specific than that because, as you can see, there are multiple triangular shapes here in this series of objects. So instead of triangular, we're going to use the word trigonal. Trigonal means the same thing, 3-sided. But we're going to throw on that word planar there because the planar is going to be our added descriptor. This is still a 2-dimensional shape. That's why it's called planar. When we move on to steric number 5, we'll see that that's not going to be the case anymore. Here we still have that same trigonal shape, but we also see that there's now 3-dimensionality to it. So it's still trigonal, but it's something different. The reason it's called bipyramidal there for steric number 5 is you can see that I have 2 different pyramids that I can form off of that triangular shape base, one going up and one going down. That's why it's called trigonal bipyramidal. So the reason we can't just stop at trigonal for steric number 3 is because it's not specific enough. There are 2 different shapes that are triangular in shape. One's 2-dimensional, we call it planar. One's 3-dimensional, we call it bipyramidal because there are 2 pyramids that form as a result. For steric number 4, we are talking about something called a tetrahedron or a tetrahedral shape. Now here we see our first instance of 3-dimensionality. Notice that this circle in the middle of the sphere kind of represents a 2-dimensional plane in the middle of that sphere. And notice that with the tetrahedral shape, the only object that is actually on the plane of that circle is the center atom. Everything else is slightly askew from it. So here with tetrahedral, we have our first truly 3-dimensional shape. With trigonal bipyramidal, we've already kind of discussed some of that multi-dimensional state for that. The fact that we've got the triangle shaped base that is planar, but we've got the two axis positions that are not. With octahedral, what we'll see is that very similar to trigonal bipyramidal, but if you look closely on this plane, we have not one, not two, not three, but four atoms in that two-dimensional plane. So we can't call this trigonal anymore. This is now considered octahedral. And the octahedral nature, octahedral means 8 faces. We could call this square bipyramidal, but octahedral is a more accurate term. What we see here is we have 8 faces that are identical. 4 on the top, 1, 2, 3, 4. 4 on the bottom, 1, 2, 3, 4. This is basically an 8-sided prism. Now, with regard to these three-dimensional shapes, I will grant to you that drawing them this way is very cumbersome in terms of you don't want to have to draw a circle and then a circle inside of it to help show three-dimensionality when it exists. So we're going to resort to another kind of drawing technique that helps show three-dimensionality. We call them dashes and wedges. Dashes show objects going into the plane of the paper. And we'll draw them just like that. And you can see examples of dashes in some of these three-dimensional shapes here. Wedges, on the other hand, are going to look, well, like wedges. We're going to call just triangles. And they show objects coming out of the plane of paper. Now, why do we use this convention? Well, once again, it's all about trying to show three-dimensionality in a two-dimensional world. And so if we were to redraw these figures, linear would be pretty easy. I've got my center atom, and I've got two different sets of bonds coming out of it at 180-degree angles. For trigonal planar, also pretty easy. After all, this is still two-dimensional. So I can just draw those three bonds forming a triangle. When we get to tetrahedral, it's a little bit more complex. Now, this diagram here doesn't really do us any favors. It actually shows it as a little bit more complicated than it is. But if you look closely, you'll see that these two are in the same plane as that center atom. So in a lot of ways, it looks like a trigonal planar. The difference is that we're going to have dashes going into the paper and a wedge coming out of the paper to show that three-dimensional nature of the tetrahedral. For trigonal bipyramidal, there are different ways of showing this. What we have to understand is that basically with trigonal bipyramidal, it's like we put together two different shapes. We put together the linear shape and the trigonal planar shape to make this shape. And 2 plus 3 is equal to 5. So there are a couple of different ways that you can draw this. You can draw it to show all three of these in the same plane. With the two positions up and down coming in and out at you. That's one way to do it, but I would say that this is the less conventional method. What is more likely to be seen is what's shown in the diagram here, where I've got three here that are in the same plane, and then I'm showing two different positions coming out. Now understand that the bond angles here are still what we'd expect them to be. Inside of that plane, it's 120 degrees. It's still trigonal planar inside of that plane. And these two positions are still 180 degrees apart, like what we would expect out of a line. The connection between the two is at a right angle, 90 degrees. But with these more advanced shapes, and again, steric number 5, steric number 6, we only see these if our center atom is breaking the octet rule. So one word of advice I'm going to give you here is that we are probably going to over-represent steric number 5 and 6 in terms of the frequency that they exist in real substances. We know that there's actually only a handful of substances that actually break the octet rule. But to feature all of the features of these shapes, we're probably going to give you more examples of those than what are really present in the real world. just so that you're aware. Most of chemistry is going to exist down here in those well-behaved, follow the octet rule, linear, trigonal, planar, tetrahedral kinds of shapes. But I do need to make you aware of one other set of terminologies. And that's unlike the previous shapes where all of the atoms in those shapes were all equal in distance from each other. And therefore, we could put anything in those positions and they would all be evenly spread. With this shape in particular, that is not the case. Those two positions on the top and bottom, those are referred to as axial positions. Axial positions exist in that linear plane. They are 180 degrees apart from each other, like a line. They are 90 degrees apart from that middle plane. The EQ positions are known as equatorial positions. Those equatorial positions are called equatorial because, like the equator, it exists in the middle of the sphere. So they exist in this middle plane. In the case of trigonal bipyramidal, that middle plane is triangular. So they're all 120 degrees apart from each other. So there will be occasions, and we're not far from them, where we're going to need to refer to the axial positions and the equatorial positions and note that they are different. And those differences are going to be important when we start looking at where to put electrons instead of atoms, because electrons and atoms behave differently in structures. All right, this last one here. Most traditional way of drawing it is showing the axial plane as being in the plane and the equatorial positions as coming out and in. Now, what's unique about this unlike the trigonal bipyramidal, at least initially, all of the positions are equivalent again. All of them are 90 degrees apart. So really, it's this one here, the trigonal bipyramidal, that's going to give us the most problems when it comes to making that difference and distinction between molecular shape and electron domain shape. Because the differences between them have everything to do with where to put electrons, unshared electrons that are on the center atom. If all the positions are the same, it doesn't matter where we put them. If the positions are different in terms of their distance apart, then it matters very much where we put them. And that's why steric number 5 is probably the most complex of those shapes. So we can see in terms of real molecules now how each of those come about. So carbon dioxide, for example, with its steric number of 2 is going to give us a linear shape. Boron trifluoride, steric number 3 is going to give us trigonal planar. Carbon tetrachloride, steric number 4 is going to give us a tetrahedral shape. Steric number 5 coming from phosphorus pentafluoride. And so we can see there is a difference here between the objects in this space and the objects in this space in terms of how far apart they are from each other. The ones in the plane are further apart than the top position to the middle or the bottom position to the middle. And then for steric number 6, we can also see in this case, all 6 of those positions are equivalent. They're all 90 degrees apart from each other. All right, let's take a look at an example. Formaldehyde. Formaldehyde is H2CO. It's a gas at room temperature. We want to use Vesper theory to predict its molecular geometry. So the first thing that we need to do is we need to start with a Lewis structure. Lewis structure for formaldehyde is as follows. Won't walk you through the entire process. But in the end, we're going to have a carbon double bonded to an oxygen and 2 hydrogen atoms around it. Our evaluation process, we first need to determine the steric number. What is the steric number of formaldehyde here? So to answer that question, we have to go back to our definition of steric number. Remember, steric number is the number of atoms bonded to the center atom plus the number of lone pairs on that center atom. Well, I've got 3 atoms bonded to that carbon, and I don't have any lone pairs. So my answer here is 3. Easiest place to get thrown off is viewing that double bond as 2 separate events instead of 1. Remember, we're not counting the number of bonds, we're counting the number of atoms that it's attached to. So this is what separates Vesper from what we did with formal charge last chapter. With a steric number of 3, we know that this is going to be a trigonal planar shape. And since there are no lone pairs on that carbon, that's exactly where we can stop. because its molecular shape and its electron domain geometry are going to be identical. So if we have a molecule that has no lone pairs on that center atom, steric number tells us electron domain geometry, and since there are no electrons to mess things up, that's also the molecular shape. Now what we talk about is what happens when those electrons are added that mess things up. Now, the reason we have to concern ourselves with this is that from a spectroscopic kind of standpoint, lone pairs don't show up as part of the molecule shape. There's nothing there. There's nothing with any kind of mass that can reflect back and show us that something is there. We know that electrons are incredibly small, but they're also incredibly repulsive. So we know that they're there. We know that they exist. But what do they do to the molecule itself? Well, so let's take a look at ozone. We've drawn ozone several times in chapter 4. We know that ozone has this extra pair of electrons on that center oxygen. So from a steric number standpoint, I can see I've got 2 atoms that I'm bonded to, plus that lone pair to give me the 3. From a repulsion standpoint, a steric number of 3 is going to give me something triangular, trigonal planar. But because this lone pair doesn't actually show anything, we can't call it trigonal planar anymore. There's nothing in that third position. At least nothing that we can see that has any kind of tangible mass. It's gone. So what's left behind is this angular shape. We call that angular shape bent. So the resulting molecule from ozone, because of the influence of that lone pair, is going to be a bent shape. Now, one other thing that that lone pair does is, because it is not shared, it's much more impactful in terms of repulsion. It's going to push harder on those bonds than the bonds are going to push on it. So this is going to push down harder. And what that means is that this bond angle, which we would have expected at 120 degrees, is going to shrink a little. How much does it shrink? We don't know. Well, I mean, we could. But there's no hard and fast rule that says, okay, one pair of electrons shrinks your angle by 5 degrees. It's 115. It all depends. Depends on what those other bonds are. So rather than speak in specifics, we're going to speak in generalities when it comes to bond angles. Bond angles are either going to be what we say they are, 120 degrees, 109.5 degrees, 90 degrees, 180 degrees, or they're going to be less than that. In this case, that lone pair there pushing on those bonds is going to make it less. So in the case of the ozone, the difference was 3 degrees. The bond angle in ozone is 117. So your book, this is material that is found in a table in your book. Your book wants you to know that there is a ranking system. I'm not going to push that on you too hard. What I want you to know is that lone pairs have a greater influence than bonding pairs. And the more lone pairs you have, the more of an influence it's going to make. The more it's going to push. So don't get caught up in this idea of, okay, well, lone pairs versus bonding pairs is one way. But if it's a double bond, it's a little bit different. And a double bond repels more than a single bond. Who cares? What matters here is that if I'm comparing bonds versus lone pairs make a bigger difference. And if I have multiple lone pairs, they make an even bigger difference still. So what really matters is that lone pairs are there. If they're there, they have an influence, they matter. So let's take a closer look at tetrahedral then. Tetrahedral, steric number 4. We're going to see the same kind of influences. Here is our Lewis structure for ammonia. Again, this is one we've probably seen before. This one was in one of your homework assignments, maybe even in multiple ones. In ammonia, you've got a lone pair replacing a bond. And because that lone pair pushes more, it's going to do two things. It's going to affect the shape. We have nothing in this top position anymore. So we have to call it something other than tetrahedral because there's no atom on the top. But what is left? Well, you know what? That kind of looks like a pyramid with a triangle-shaped base. There's trigonal pyramidal right there. That's the origin of that name. So again, why can't we just call it triangular? Because it's not specific enough. So we saw trigonal planar and trigonal bipyramidal in our domain shapes. Now we see trigonal pyramidal where instead of having a double pyramid, it's just the one pyramid. Notice what happens to the bond angle as well. In tetrahedral, bond angle is 109.5. Here for the ammonia, it's 107. For water, same thing. But now I have two lone pairs instead of just one. So all that's left is this angular shape here, which again, we call bent. What happens to the bond angle? Well, it shrinks some more, 104.5 in the case of water. Now, as I mentioned before, I don't care that you know that ammonia is 107 and that water is 104.5. What I want you to know, what I want you to draw out of this is that the presence of that lone pair is going to shrink the ammonia. The presence of those lone pairs are going to shrink the water. For a quiz, for a test, for a homework, less than 109.5 is going to be all that you need to know. You don't need to know the specifics. They're really not important. And the main reason they're not important is because there's no way of monitoring, okay, if I have H2S instead of water, am I going to get the same exact bond angle? Answer is no, I'm not. That sulfur is bigger, it's going to have a difference in the bond angles. There's no hard and fast rule. We can't say each lone pair takes away 3%, or each lone pair takes away 4%, or whatever. There's no hard and fast rule for that. So we're going to speak in generalities here. When it comes to steric number 5, I said before, this one's going to be the tough one because unlike the other ones, the placement of the lone pairs is going to matter because the positions are not equal in distance from each other. Now, conventionally, in these other two examples, we have shown lone pairs as missing from the top. But it doesn't have to be that way. If you showed a three-dimensional shape that had a hydrogen up here and a lone pair here, that would be okay too. The 4 positions are equivalent to each other. They're all the same distance apart. But with this one, they're not. So we have to be picky about where we put those lone pairs. And the pickiness is this. They have to be in the equatorial sites. That's why we named them different things. The reason why those equatorial sites are 120 degrees apart. The axial sites are only 90 degrees from the equatorial ones. So there are 3 different subshapes that come out of this because there are 3 different equatorial sites. If one of those sites is occupied, we call it seesaw. Now, it's not as easy to see. I'll try to bring a molecular model with me on Wednesday. We've got a couple over next door. I'll try to bring those with us, and you can kind of play with it and see how we arrive at some of these names. But more or less, what happens is if I take that site off of the equatorial plane there, what I basically get is if I turn it from this way 90 degrees so that the axial positions are horizontal instead of vertical, those 2 remaining equatorial positions basically become the legs of a teeter-totter. And the axial positions become the teeter-totter itself. So that's where seesaw comes from. The impact of seesaw is 2 things. Those bonds, which were 120 degrees apart, shrink a little bit. And this 90-degree angle that existed between axial and equatorial shrinks a little bit as well. So our bond angles get kind of crunched a little bit because of the lone pair there. If I have 2 lone pairs, again, both of them going into equatorial positions, what is left? Is a T. The molecule here is called T-shaped because all that is left is the linear position and one equatorial position that is exactly 90 degrees in the middle. It's T-shaped. Bond angles here are slightly influenced, so we are still going to call them less than 90 degrees apart. If all three equatorial positions are occupied, well, that means that there is no more equatorial plane, basically. All that's left is the line, the linear shape. And those three positions basically cancel each other out. So any pushing that they have on those two remaining bonds is basically negated by the other two lone pairs. So we keep this at 180 degrees. We don't need to put the less than there. So like I said, this is the one that's a little bit funny because unlike the others, this one, it matters where we put them. When we go to steric number 6, again, everything's equal. So where we put that lone pair really doesn't matter initially. Conventionally, we put it on either the top or the bottom. Conventionally, we use an axial position. And the main reason for that is if a second lone pair is necessary, it does matter where we put it. They have to be opposite each other to negate each other's effects. They cannot be next to each other because then we're running into the same kind of situation that we saw with steric number 5. So when one position is taken up, we get square pyramidal. Bond angles here are all slightly influenced. They're all less than 90 degrees. For square planar, the two lone pairs basically cancel each other out again. So the bond angles in the square plane are 90 degrees apart again. Now, if you are worried that I have just thrown a ton of your information your way in the last 40 odd minutes, you are absolutely correct. I have done just that. Luckily for us, pretty much everything I've said in this long-winded attempt to explain three-dimensionality to you in 40 minutes can be summarized in a series of relatively easy to read tables. And here they are. So these tables are directly out of your book, and you'll receive a version of these tables, actually a slightly modified one, for your Chapter 5 quiz and for the exam that comes with this bank of chapters. But understand, this puts everything kind of in perspective here. So what it really comes down to on your part is drawing the correct Lewis structure and interpreting that structure correctly. How many bonding pairs, how many bonds there are, getting the correct steric number, figuring out how many atoms there are bonded, how many lone pairs there are, differentiating between the two to get the correct geometry and the correct bond angle. So the left-hand column here, those are your electron domains. They all come back to steric number. Those shapes have everything to do with how many lone pairs there are. And again, notice, as far as the bond angles are concerned, we don't mess around with trying to figure out exact numbers if there's a lone pair there. We just say that it's less than whatever the base value is. And so, again, this table here gives you kind of that idea of what it is that you're going to need to do. So I presented almost everything today more from a conceptual basis so that you knew where all of this came from. The more important thing is applying it.